Welcome, everyone. So I'm Geordie Williamson. I'm the director of the Sydney Mathematical Research Institute, which is hosting this event. And before we begin, I'd like to acknowledge the Gadigal people of the Eora Nation, on whose ancestral lands we find ourselves today. Welcome to Science Week. So it's really a great pleasure to have Holger Dulin here today. So Holger did his PhD in Bremen in Germany. He did postdocs in Loughborough and Boulder, and then he came to the University of Sydney in 2008. At that point, I was overseas, and I remember at some point, saying that I'd done my undergraduate at the University of Sydney, and someone said, "Oh, that's where Holger is, the somersault guy." And I can't imagine this guy that was doing somersaults down the hallway, as you can see here. So I don't know what he's got in store for us, but yeah, we're very excited to have Holger speaking to us today. So one more thing about Holger. Every time I talk to Holger, I learn something interesting. And that's a wonderful property of a person. So thank you very much, Holger, and we look forward to your talk.
Thank you very much for the kind introduction, Jordy. And I must disappoint you that I am definitely a theoretical diver, not a practical one. I think when I stood on the 10-meter board for the first time, I took the stairs back down. But I did get very interested in this from my background in mechanics. So there was a research project that had the following participants. So there were the 3 PhD students at the top, then academics from different sources. ACFR was involved, the Math Institute, the Sports Science Department. And we had as our industry partner, the New South Wales Institute of Sports. And so we actually were in the amazing situation to work together with 2 of the best athletes in diving, Matthew Mitchum and Alexandra Croak at the time. And let me start by showing you one of the dives that Alex did. So this is a twisting somersault, as you could see. So the point is that when she takes off, I mean, there's always debate about this, but my point of view is that she takes off without twisting. So just going backwards into somersault. And then she starts the twisting a little bit later with her arm motions, and I'll show you slow motions of that, but I guess it's maybe good to see not too much in the beginning. And here are some more shots in the Olympic Diving Center in Sydney. When we started this project, I mean, I would just go there and watch these guys and sit at the sideline for an hour, also see the interaction with their coach. And well, we wanted to understand better how they do what they do, and maybe also be able to improve what they do or suggest something new, and I'll come to that. So let me start with something slightly simpler, which is a cat being dropped. If you don't like your cat, you can do this at home, right? So you hold the cat upside down on the legs. So the cat is not moving at the moment when you let it go. And then the cat will roughly do this. And the cat knows how to turn itself over in midair without having any way to push itself off or to have any torque involved, right? Just by change of the body shape. And lands on its feet. And so this is a situation where this shape change is extremely important. And that will also be important for the twisting somersault. But before I go there, I want to look at somehow simpler situations. And maybe the simplest situation you can imagine is that you're floating in free space. It's simpler. It's kind of like the cat, because the cat falls because there's gravity on the Earth, but the astronaut doesn't even fall. It just floats. And let's not talk about changing orientation. Actually, astronauts also know how to do that, and I'll come to that later. But I just want to move. The astronaut wants to move. Right? And how do they do that? By losing mass, basically. And they don't, I guess you could do that if you're floating in outer space. Maybe you could get rid of your shoe and throw it, right? And then by conservation of momentum, and these conservation laws are important in my talk, so I'll just throw that at you. I throw the shoe at you, and as a result, I will go the opposite direction. And astronauts need their shoe, so they have these thrusters, which actually does that for them, right? It ejects mass at high speed away from them, and then they move in the opposite direction, right? So that's one way that you can generate a motion without, well, having any way to push yourself off. And that's also the principle that is acting in rocket propulsion. I mean, the rocket, the most important thing about the rocket is that it throws fuel out at high speed, right, in the opposite direction. Okay, so that was a simple example. This is just an aside, but it has to do with losing weight as well. So could the Airbus A380 fly from Sydney to London direct? So you just need to look at these numbers here. So the airplane is, when it's empty, it's 280 tons. It has a really big fuel tank, which when it's full weighs roughly the same as the empty plane, 250 tons. And it also has a maximum takeoff weight, so it can't be heavier than 560 tons. So the payload is 65 tons, and that's roughly 500 passengers. So if you want to fly to London, unfortunately, you need a lot of fuel because it's far away, and the plane is even heavier because it needs all the fuel in the beginning, and so it needs even more of it. But yes, you can do it, but you won't be able to take a lot of passengers. Right? So I guess there's a trade-off. It will be expensive, right, if this will be done. About losing weight, there's this aside that a plane also has a maximum landing weight. And for this plane, it happens to be 390 tons. And that means that after takeoff, landing is actually impossible. And if there is a medical emergency, let's say, that forces the plane to have to land, it can't until it loses lots of weight. And both options are bad. I mean, you don't want to get rid of the passengers, obviously. So you have to drop the fuel, right? And luckily, it's volatile. And if you're high enough, it evaporates before it would hit the ground. But that is unfortunately actually necessary, but it doesn't happen very often. I thought that was worth the detour. Now let's start talking about rotating. So how do you rotate faster? And yeah, maybe you could also lose mass, but that's not really an option for an athlete. So what you do instead is you change your shape. Right? And this is a very well known course, and you've seen this before. This was actually a particular world record attempt, fastest spin on ice skates in 2006. And well, if you look at this, maybe I can play it again. It is quite amazing how fast she is spinning in the end. In the beginning, you notice also the leg is also stretched out. So that initially the idea is to make your body broad. And then when you pull in, you get faster and faster. And so initially, arms and legs are stretched out. And in the end, they're pulled in. And the increase in the speed of rotation is about 8 times. Well, if you do it at this level. And so the important thing here is that you're not changing your mass, obviously, when you do this, but you change what is called the moment of inertia. And that is like mass, but for rotation. And let me show you a few formulas and explain why this works. So really what is behind here are conservation laws. And the first one with the astronaut we've seen is mass times velocity is a constant. So if you lose mass, you can get more velocity in some rough sense. But the interesting one for us, and here watch the size of the letters in the video, is that in this setting, we have moment of inertia times angular velocity, and that is a constant. So if you can change your moment of inertia, which is what you do when you pull in your legs, your arms. Because the product has to be constant, then the angular velocity will increase. And since it was roughly a factor 8, I mean, so I guess now we could try to compute the moment of inertia of maybe a body that starts, don't break my leg, maybe like this. And that's an undergraduate calculation, right? What's the moment of inertia of this? And then compare it to this, and probably won't be quite a factor of 8, but somewhere near that. Okay. Stephen Hawking said in his book that every formula halves the sail. So I won't have too many formulas. So I have 2 so far, and I'm trying to get away with 2.5, let's say. There will be another important formula, which is the last one again, but it will be slightly different, but also slightly the same. That's why it only counts for half. So I hope you will remain here until the end of the talk. Anyway, so these conservation laws exist because there is an underlying symmetry in this physical situation. And for the astronaut, that is translation symmetry. So when the astronaut, well, since there's no force at all in outer space, if you move the astronaut around, basically nothing changes for him. That's actually even true when you rotate, but let's ignore that. So the potential energy of the astronaut is independent of the position because it's 0 wherever the astronaut is. So for rotations, it's a bit more interesting, but the same principle. So the potential energy of the ice skater, of course, we're ignoring that there is ice and a skate and all these things, but roughly is independent of the rotation of the skater, because your potential energy only depends on where your center of mass is, right? And when you rotate, that's not changing. Well, when you rotate like that. Later, we'll see that it does actually change. Okay, and so we said, well, these things are constant because there's a symmetry. So what are these constants called? The first one is called momentum, mass times velocity, and the second is called angular momentum, moment of inertia times angular velocity. Okay. Oh yeah, and here's the formula that will appear again in a different way. So later, when I come to the divers, I will show you what a dive looks like from the point of view of the diver. In some sense, of course, it might be very confusing if you see the world rotating around you, but in some sense, this is a simplification because we are going into a frame of reference, which is rotating, where we remove the symmetry, right? If you're the diver, and this is actually true for divers, in a way, they don't know their orientation in space while they are falling and rotating. And that's why this is called spotting, why at some point they open their eyes to actually see what their orientation is. So from their point of view, this a part of the rotation, and I'll explain which part of the rotation they can't perceive, that's exactly this special frame that we're going into. Okay, a little bit of history. So these ideas of conservation laws are related to symmetries, and Sophus Lie was a Norwegian mathematician who lived in the 19th century. He lived a very unhappy life for reasons we don't fully understand, but he was very prolific also. He created by himself, basically, this theory of continuous symmetries. So these 2 examples of translation symmetry, rotation symmetry, you can generalize in a great way, and that's what he did. So now we call these groups groups. And why are they called groups? So a group is a mathematical object or a collection of objects. When you take 2 of them, you can combine them, get a new object, which has a similar property, and I'll show you with translation. So if I translate myself in this direction, okay, that was one translation, and now I translate myself in this direction. And then if I do one and the other, if I go back to where I started, right, then that's also translation, right? But it's a translation in a different direction, right? I added the two together, right? And so this is kind of a very simple example of a group of operations. And this word group is saying if you combine them, you can get an element of that group. And you can also do it backwards, which is what I just did, right? So I was here and then I walked backwards here. So that's the inverse operation that gets me back to where I started. So that's basically the definition of a group. But anyway, this is not too important for us. Let's think about things that are moving in space. But no, I want gravity now because I want to go to the divers. So what I want to understand is something like a diver. This is a diver that's not changing shape and flies kind of in a certain way. You see there's some kind of tumbling motion, which is complicated. But the thing that is simple is the motion of the center of the object, right? The motion of the center of mass of the object. And the center of mass, and that's why there's this bird here in the video. Okay, looks like this. A bird with stretched out wings, fairly heavy wings, in fact. So it's probably not a real bird, but this is made from wood. And it's made so that you can balance the bird on its beak. Okay, so here we go. I guess maybe you can see better like that. And it's actually fairly stable. And this point of the bird is its center of mass. It's the point where you can balance an object. And luckily, that point is still inside the object, which is why I can do this. But you can imagine easily objects like a ring, which has its center of mass in its center, which is actually not part of the object. So you can't balance the ring. Right? But still the center of mass of a ring would be in the center of the ring, but it's not part of the object. Anyway, it doesn't matter. So here is the center of mass, the bird. And when I throw this bird, which I won't do because it's already kind of wobbly, then this point will move on a parabola, no matter what the bird itself does, right? So the bird does something complicated, tumbling motion, but the center of mass moves in a simple way. So the center of mass moves like a projectile, so like a point, let's say, or a ball that you throw, right? They move on parabolas. And if the object is complicated, it doesn't matter. The center of mass still moves like a simple ball. So that's the first thing. This is not quite a symmetry. Oh, and in fact, yeah, why not? I mean, because the motion up-down, this parabola, is not a symmetry because when you change your height in the field of gravity, you change your potential energy, right? So the translation in X or Y, that's a symmetry, but the translation up is not. But nevertheless, what happens in that direction is also not too complicated. It's described by a parabola. And we understand that, and this is surprisingly maybe true, even when the object changes its shape, right? So the diver, right? So they dive off their board and then they do something complicated. But at any moment in time, they have a center of mass, which is changing if they change their shape. But that imaginary point will move on a parabola. And that's why we just kind of ignore that, right? So we'll just say, okay, let's get rid of this. It makes it very hard to understand. So we also move into this special frame of reference that moves with a center of mass. And then we just have to understand the rotation around that point. But anyway, so every center of mass moves on something like that, right? Okay. I wanted to demonstrate conservation of momentum before I come to the tennis racket. Anyway, so here is an object, and it's not moving at the moment. And so when I move around, it moves with me, right? And in particular, the axis, you see this is something that has a symmetry axis that's pointing at you. When I move, then this axis points in a different way. Now it points to the board. I guess you see the back of it. Now it points that way, and so on. Okay, so this is built so that you can give it a lot of angular momentum. So now it's spinning very fast. And now I'll do the same thing. So I will try to turn it, but it doesn't turn, right? It just keeps pointing at you no matter what I do. And so that's, oops, well, it gets slower because it does have the string, which slows it down. This is an example of conservation. Now it points in a slightly different direction when I spun it up, right? I mean, I can change this direction. But if it's just spinning and I try to turn it, I can maybe go all the way. Then it's still pointing the same direction. So that's conservation of angular momentum. And one thing that you see, oops, maybe other way, is that this is actually a direction that is conserved. Not only the magnitude or the speed of the spinning is, but the direction of that spin is constant. Right? And then, of course, people do this. Oh, okay. That was hard. Yeah. All right. So that's the Diavolo. And so the important point, I mean, I wanted to do it a bit earlier, but say angular momentum conservation is not just preservation of some kind of object or quantity that has a size, but it's also a direction. And that will be important when we come to the actual divers. Okay, so now let's get closer to where we want to be. So we want to look at rotating objects while they fly in space, and you forget or you should ignore the part where they actually, the parabola that they do, because that's just what they do unless we're in outer space. And so here I have a tennis racket, and there are, and I don't want to do that with a tennis racket, but I kind of threw this thing in the air and it just kind of tumbled. And you can do that with any object, but it's hard to catch them, so I won't do that. But if you throw them in the right way, then it's easy because they will just not tumble and they will just rotate in a simple way, like this. And each object has 3 axes, they're called the principal axis, about which they can perform this simple rotation. So no tumbling, just rotation about a fixed axis. And what I want you to pay attention to is this funny symbol here on the racket. At the moment this is, seems irrelevant, but it's the same when I catch it. Right? Okay, so now I will throw it in a different way. But first I want you to look at the symbol and remember whether it's like this or like that. Right? So it's not symmetric. And I'll try to do the same as what I just did. So just throw it in the air and catch it again. This was probably not good because maybe I didn't tell you what it was in the beginning. Okay, so now, remember what it is now. Okay, and then I will ask you whether it has changed or not. Okay, let's do this again.
Yes.
Change. Okay, let me do it again. Maybe I'm just up. Yeah, this was bound to happen. Not trying hard enough. Okay, let's try it again. So remember, now I will throw it up and changed. It will happen almost all the time. It is, of course, possible if you practice this a lot, but I can't throw it that it will do this and not flip. I would like to throw it so that it just does that, but whenever I try that, I invariably get the other flip as well, right? So I get a twist for free, right? So it's kind of the dream of the somersaulting twisting diver, right? So they do a somersault, right? Somersault is this, and they get a half twist for free without doing anything. Right? Okay, half twist is not a lot, but anyway, the point is that this motion is unstable, right? While this motion is stable. I mean, so yeah, I mean, I guess I can show it to you, then put it like this, and then flip it and show you again, and this will be the same. But if you do it like this, then it will almost always change. I suggest you try it yourself. It's hard to believe. And this is the experiment that I won't do, actually, but Of course, you can do that with any object. And mobile phones are also kind of things you can throw in the air. And they will do the same thing. So if I throw it actually like this, when it comes down, it will be like that. So I mean, I would start like this. And yeah, everybody can do that themselves, but I suggest to do it over a bed or something like that. So it will come like, but it will not come back like this, but like that. Or books, right? It works with many objects. With the phone, what is interesting, if you're really getting into this, there are apps that actually record the orientation of the phone, right? That's why the phone always knows which way it's pointing. And you can basically start this app and it will record what happens in the air, right? And then you can look at this recording and it will, well, just verify to you that it's not just this happened, but it flipped over the other axis as well. So this is always the axis of intermediate moment of inertia. So I told you everybody has 3 of these axes. One has a large moment, one has a small moment, one has a middle moment, and the middle moment does this behavior when you try to rotate about that. Of course, some bodies don't have a middle moment because maybe their largest and second one are equal. That's what happens for rotationally symmetric body, like this one here. That has only 2 different moments. Okay, sorry, these are the things that I think I try to explain now. Intermediate axis is unstable. And here's a interesting video of the same effect. So this is on a space station. And this astronaut is this kind of, it's like a wing nut, really. It's something that's screwed onto a screw, and he will just turn this and it will unscrew itself and then it will start flying. But then periodically, it will flip itself over because it is rotating about its unstable axis. And even though it was very well kicked off because it was sitting on the screw, so it rotates very symmetrically, and then theoretically it would stay there forever. But there's a small error, and then it's unstable and it flips itself over. This is called the Zani-Bekov effect. It's probably not true that what the stories that are in the internet, that when this was discovered in the Mir space station, that they kept it as a secret for a few years because they thought it might be relevant for the Earth flipping over. Because this is actually very well known since 1700s, but it's a good story, I guess. Anyway, so that was the Euler top. The Euler top is a rigid object that is in free space or on the parabola if we do it in Earth. And Leonhard Euler was the person that first wrote down the differential equations for this. And he lived another 100 years earlier than Lee. And he was extremely prolific. He wrote about 900 papers. And you can see in this portrait, it's not a failure of the artist, that one eye is basically closed, right? So he lost his eyesight, and he was blind, I believe, from 1766. But it didn't stop him, except he had to dictate his papers. So he wrote papers faster than most of us can read them, also in 3 languages, of course. That was mostly Latin, of course, French, German also in his work. And he's the master of us all. And I want to show you a tree of this is the genealogy in the world of PhDs, because every PhD maybe only has a single parent. It used to be actually a tradition to have 2 advisors, so then you had 2 parents. And then you can ask this question, who was whose advisor? And here's a part of this tree. Actually, the link between Euler and Lagrange is probably a little bit questionable because Lagrange was mostly self-taught. But in some sense, and I don't think he ever made a PhD, but in some sense, Euler was his mentor, I guess. So maybe this is not a PhD link, but all the other links are links of PhD advisors. And so in this database, there are about 300,000 mathematicians, and 150,000 of them are descendants of Euler. Right? Of course, over many generations, I guess maybe roughly 10 to 20 generations from back then. But that's why I say literally the master of us all, well, master of half of us. Therefore, it's maybe not a great surprise that when I trace my lineage to my supervisor, Peter Richter in Bremen, and his Grossmann in Marburg, and so on, that at the end, well, at one end of this tree, or in somewhere in this tree, of course, it continues back further, is Euler. It's a good way to do genealogy because the data is reasonably good preserved, right? Because universities have records of who did his PhD with whom and so on. So it's relatively easy to find these things. Anyway, another little aside about Euler. He was also a popular science, science popularizer that came with his job. I guess he was employed at some point in his life by the King of Prussia. And as such, he was some kind of tutor to this princess of Prussia and was a private tutor. And since he was in St. Petersburg most of the time, I think mostly how this worked, it was not over Zoom, but by writing letters. And the 74th letter, which you can see here, at the top, it says 74. Brief, which means 47th letter, so it's not a very great title. And then so wie man von einem Körper, solange in Ruhe ist, fragt, etc. So I guess this is basically what I explained to you so far. No, I'm joking. But anyway, this was some kind of popular science. Of course, now we're more popular. This was kind of very much restricted to the royalty at the time. And it's good that it has changed. Okay, so now let's come back to diving. So here's Matthew Mitchum. And yeah, I think this is a kind of famous dive. I think it might have been the highest scoring dive ever. I'll explain the scoring a little bit later, but the scoring is a product of some number that the judges give and the degree of difficulty of the dive. So if you do a simple dive well, that's not good. And if you do a hard dive badly, that's also not good, right? You have to do a hard dive well, right? So that both numbers are high. The product has to be high. And that's what made him win the gold medal, actually. Okay, so this is about coupled rigid bodies, and I brought a couple of coupled rigid bodies here, 3 of them. So these are, actually at the moment, they're not pendular, but well, they're just metal rods, and I arranged it so that I can put this in any position I want. So basically, the weight of this is balanced by this weight and so on. And that's why when you give it a kick, I mean, it's kind of pleasant, but it's not too interesting. These rigid bodies, the way that they are arranged now, each one moves in a way independently of the other. Of course, they're forced by these pin joints, right? So there's a pin joint here and a pin joint here. And so they all carry themselves with each other, but the rotation of each one seems to be independent of the others to some extent. Anyway, I just wanted to start with something simple because now I want to make it more complicated. And so I won't lose weight, but I'll add weight. And then I will show you that this system of coupled rigid bodies, it's just 3 rigid bodies that are connected through a pin joint, is actually very complicated. Actually, my advisor, he had a machine like this in his office, and that's probably why I'm standing in front of you now, because I thought this is so fascinating. It's such a simple system. Actually, if you have only 2 of them, it's already complicated enough that if you give that a little kick, then the motion is very, very hard to predict. Right? So this is an example of a chaotic system. And I'm just using this as an excuse to show it to you because it's not much related to my talk, but the little connection is the following. That the divers are exactly not like this, right? So here I have coupled rigid bodies, and they do a free motion in the field of gravity in the way that they have to do according to the laws of the motion, right? But the divers don't do that, right? I mean, they don't flop around with their arms or knees, but they control them, right? So there are muscles, and so the shape that the diver has is completely controlled, right? And so this would be like having a muscle here and a muscle here, and then the diver would just say, no, I mean, now you're doing this, right? And it would not be just the free dynamics that you see, but you would see what the diver wants, right? So the diver actually has full control over the shape, and that's how then he can control, or she, the orientation. Okay, so this was the triple pendulum. And the other point, of course, is that this is a system of 3 coupled rigid bodies. When we model the divers, we model them like this. I mean, so like a system of coupled rigid bodies, but where each segment of the arm, let's say, or the leg and so on, is itself cannot do any shape change. The only shape change that is possible is through the fact that we have joints. And that's a little bit of a simplification. Otherwise, it's more like Odo the shapeshifter, right? I mean, they can just kind of completely change their shape, right? We don't want that, right? That's too hard. So let's just do coupled rigid bodies. Yeah, which brings me back to the astronauts. So this is actually from a scientific paper from the 50s, I believe, the beginning of space flight. And the question was when the astronaut, I don't know, maybe forgets his tether or ruptures and the thrusters are empty, and he wants to wave goodbye to the space station that's behind him. I mean, I guess could turn his head, but I don't know. But can he turn around? Can she turn around? Well, so it's kind of that's like the cat, right? So and this scientific paper said you have to do the following thing. I'm sitting down so that gravity doesn't pull me down, right? So that's just to support me against gravity. But otherwise, as the astronaut, you're supposed to move your legs in a particular fashion. I'm not touching the ground, but that's basically what the paper says. And it's quite hard work, but I made a quarter of a turn, right? So that way you can change your orientation. And yeah, this is what the astronauts also had to learn, right? Before they can go out in space, so that they're always able to wave goodbye when they get lost in space, right? Anyways, okay, so we're getting closer to our final dive. So here's Matthew Mitchum again in slow motion. And so torque free again just means that there is no force acting other than the thing that pulls us down, but we already got rid of that center of mass. But there's twist, and it's with angular momentum, because let me show it again. When he takes off, then he pushes himself into a somersault motion, but at the same time, almost at the same time, also into a twisting motion. And I want to keep those two separate. And to make that a bit simpler, let's look at a very simple model. And indeed, it's quite surprising, at least I did not think this would be enough, but to model most things that we've seen in these videos, it's enough to move one arm. Okay, so that's the simple model. So a rigid body, which is the torso, the head, the legs, one arm, and we just move one arm up and down. That's the only thing that the diver needs to control, in our simulation to achieve something. So here's now a computer simulation of this one-arm diver. That's the one-arm diver, and let's maybe count together. So this is 3 half somersaults and 6 half twists. So maybe first we'll count somersaults. Okay, somersaults, you can just look at the head basically, right? Spinning around like that. Okay, so, oops. Okay, we start up. Well, that's why it's half somersaults, by the way, right? Because in the simplest dives, you start upwards and you enter the water head first, and that's why it has to be half a number, right? Half an integer. Okay, so head down, so that's half. Head up, 2, and head down again, 3. So that's 3 half twists. Sorry, what did I say? 3 half somersaults. Okay, so they are relatively easy to count. So for the twists, it's maybe easier to count full twists. So this claim is that this is 3 full twists. So the twisting starts now. This was 1 and 2 and 3, and then it stops. So it's a bit tricky to observe. Every dive has a number like this one, which I just want to focus on these middle numbers, 3 and 6. That's the number of half somersaults and the number of half twists. And the rest is telling you about some other things, for example, twisting and forward or backwards. And then based on this number, which they have to announce, there's a degree of difficulty, which you can look up in the FINA tables. And then the score is made by multiplying that degree of difficulty by what the judges say. Anyways, so once they are in the air, the only thing that they can do is change their shape in order to change their motion. And in a simple dive, that's just somersaults, that's like ice skating, right? They will just kind of curl up and rotate faster about this axis. But we want twists, right? So, but it's the same. I mean, you have to change your shape, but you have to do something asymmetric, like move one arm, right? That's why we need an arm to do twisting. Well, and overall, what is possible is determined by what shapes are possible from the human body, how fast you can change things, and how accurate you can do these things. So this is the same dive as before, but the arm motion came a little bit off. And as a result, the twisting motion does not stop. So this is almost the same, well, it is the same shape change as before, just at a different time that is off by a little bit. And so the timing is also crucial. All right, so this was a little too early with the arm up. So here's my third formula. It's again the same, angular momentum times angular velocity is, moment of inertia times angular velocity is angular momentum, right? What we had before, I times omega is L for the ice skater. What changes now, which makes twisting possible, is that we are actually in 3 dimensions. And so, and I explained that the angular momentum is a vector, right? That was the axis of this thing. And that's the thing that is constant. It's not only the length, but it's also the direction of that vector. But when you change I now, what can and does happen, then omega, which is the angular velocity, which tells you how you rotate in space, will also change. That's the same, but it will also change in general its direction, not only its magnitude, right? And that's how the twisting is actually initiated. So that's the point here. So the direction of this omega, which is also a vector with 3 components, as written there, that may change, and in general it does for the twisting dives, and that's how it is generated. If you don't know how to multiply a vector to a matrix, don't worry. Okay, symmetry adapted frame of reference. So now I want to make it a little bit easier to see what's going on. So on the right picture, you see what the diver sees while in free air. And so here is the diver. And this one has this little stick here, which is the angular momentum vector. So if you jump off the board like that, then you're rotating about this axis. And so the angular momentum is pointing in that axis. So that's this little stick. And now imagine you do your dive, and at any moment in time, you look at the tip of this vector. That's the adapted frame of reference. And then you will see a motion of this point from that point of view. Well, actually, if you look at it, again, it will be just to your left, right? It hasn't actually moved at all. But if you do this, for example, then you see, oh yeah, now this point is different relative to me looking at it. So the rotation about this axis we're going to throw away, and we're just going to display that point. And that's the point that you see on this sphere. And now it's easy to count how many twists there are, because it's just the number of times this point goes around the sphere. And it's the same dive as before, 51360. So that's 3 dives. And you end and start at the same point. That's why, well, if you do that, then your entry is perfect. All right, I want to finish with our new dive, which has never been performed, and it's probably also not clear whether it can be performed. So we have not managed to succeed the athletes and coaches in our team anyways to try it. So this dive is 513XD, right? So, and the X is 10. So that means 10 half twists, so 5 full twists. And hopefully you will see this dive at some point in the future. Maybe Australia winning the Olympics with it. And here, maybe first look at the point on the sphere because it's easier. So you see kind of 2 types of circles there. So what happens, diver goes in like this, does this, as before, that brings him to the first circle. And then she does this. Now I'm moving both arms, by the way, yeah. So this is a thing with 2 arms. That brings her to the second circle where the twisting is even faster. And then you have to stop that twisting, go down to the first circle. And then you have to move that arm back, so for entry. Right? So not too bad, like this, 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 right? And each one at exactly the right time. And and now maybe you can look at both figures and try to count the number of twists. And you see the twisting in this phase is extremely fast. That's why the timing will be extremely hard to do. Of course, also when you twist super fast, it will be a lot harder to move your arm, right? So it's also, I mean, I'm just saying, oh, you just change your shape, you have muscles and so on, right? I mean, this is hard work for the diver to actually do that and to do it in a very short time, right? So these change shapes, the way we model them, they have to take place very fast. And that's also not clear whether this is in the humanly possible limits, but it's somewhere on the edge. So there is hope. So I want to just finish to show this slide again. Thanks to the team of all the people that were involved in this research. And thank you for your attention.
So thank you very much, Holger, for this really beautiful talk. So does that final dive have a FINA rating?
No, I don't think they have tried to rate it yet. I mean, we published this. I mean, it's an actual publication in the Springer Journal of Nonlinear Dynamics. And it has, I mean, if you want to read more about it, you just Google 513XD, right? I mean, that's essentially unique. No, but I don't think they have even created a rating. There are people that are into this business of actually computing ratings because it's also somewhat subjective. So there are that make computer models and then say, oh, this dive should have this rating, right? But yeah, no, I haven't heard of any of that, but that's a good thing. I should try to follow that up.
So there's some questions on Slido. Are there additional forces at play during a dive like gravity that make it harder to move your arm, perhaps depending on orientation?
Yeah, I mean, so I guess I just mentioned that in the end. I mean, it's so the external forces are just gravity. So that's simple. That's just the center of mass. And I think one thing I forgot to say is what makes diving hard is that it's only 10 meters, which means it's only 1.5 seconds roughly. So whatever you do, you have to do in 1.5 seconds. If you look at aerial skiing, for example, where they jump off big ramps with high speed, so they have maybe 3 seconds or 3.5 seconds in the air. And because they have so much more time, they can do so many more things. But anyway, but to come back to the question, yeah, but what I mentioned is that if you want, that's a centrifugal force, right? I mean, yet if you rotate fast, then it's harder to move your arms. Yeah, so those are additional forces that are absolutely relevant for the diver. But But for our computer model, we just said, yeah, move the arm up, please. But yes, that will be hard, and it is relevant. That is probably maybe too hard. Yes.
Precise is an Olympic diver's timing.
Yeah, so again, I mentioned this, right? So the timing is crucial when you do these things wrong, and when they learn new dives, they do get this timing wrong. That's actually why the coach is very important. And I don't know how the coaches do it, but they sit at the side and they have a call basically. So it's a call out when they learn a new dive, which when this call out comes, it just says stop whatever and open up. And so that you will enter in a reasonable way, right? I mean, not completely on your belly or something like that, right? And so the coaches have apparently enough intuition, I guess, and then the divers can react to that call so that they do open up. But on the other hand, they also put bubbles in the water and to make it softer to land on, which is still pretty hard if you get an entry wrong. So to be honest, I cannot totally answer that question. Yeah, so I think they are very precise. But this is also debate that's going on more in the sports scientist community, which of course somehow criticized us because, yeah, you mathematicians who don't know anything about the real world. And that's probably true to some extent, but it's a challenge maybe. Yeah.
So one question was, how does the sensor in your phone work? How does the rotation sensor in your phone work?
That's actually a good question. And I don't know the answer. I guess it's probably a gyro sensor, but whether, I mean, it does detect the magnetic field, but I don't think it is just the magnetic field. So it measures acceleration, but yeah, no, that's a very good question.
Are there further questions? Yeah, after that.
You just mentioned ski jumping. How close is the maths between diving and other forms such as ski jumping?
Yeah, so I think the math is quite similar, and we always kind of had this still in the back of our mind to say, well, maybe we should move on to aerial skiing in particular. I mean, ski jumping, the traditional ski jumping is relatively boring, right? But aerial skiing is a different story. But the modeling would be quite similar. Maybe you want to model the legs and the skis as well, I guess, because they're heavy. And then you can do things like that while you're in midair, and it will have a big effect. Yeah, but I think from the point of view of modeling, we understand the situation well enough that we could tackle a different sport. But then the details are, of course, will be different. Yeah. So all the simulations that you saw, they were made so that they take 1.5 seconds if they are played in real time. Probably we slowed them down because otherwise you can't see anything. But in the simulation, it was always 1.5 seconds because that's the time you have when you jump from the 10-meter board. So somehow the speed of the spinning is just related to your change of your body, right? And so that's this kind of windmill motion, which if you do it at the right time, will speed the spinning up, and then you can achieve 5 full twists, possibly. Yeah. Yeah, that's a good point. Something we neglected. Certainly for the motion of the center of mass, it's irrelevant. But where you could speculate, and it's probably true, that when you get to these really fast arm motions, then air resistance will also be an extra hindrance. But I think for the description of the dynamics of the rotation, I think the effect of air resistance is probably negligible. But yeah, but that's a good point. I mean, that's of course another thing that at least I'm so used to ignoring or neglecting that I don't even notice or mention it. But thank you for pointing that out. Yeah.
So maybe final question from Slido. What happens if a diver is not able to slow down from the fast part of the twisting?
It will hurt, I guess. And that was also the reason, I guess, that actually there was some more resistance from the coaches, because they said, look, you're an Olympic level diver, right? And you have trained to get here for whatever, 5-10 years or something. Do you want to risk trying this crazy thing and injuring yourself? Or do you just want to keep doing what you're doing? I mean, so that was, I mean, literally basically what I said. I mean, the athletes were a bit more open, kind of gung-ho, I suppose, but the coaches said, oh, be careful. You know? And the coaches have a lot of say in this. Anyways.
So thanks, Hicks, for this really lovely lecture. And yeah, please join us outside and let's thank Holger again.